in soft matter electronics. So the introduction and the outline of my work. Well, the work was done predominantly by a group of postdocs that are very, very, very talented. So these are non-trivial experiments to run. These are not things you just go in and shoot a laser at. Getting at these buried interfaces requires a lot of work. So Lou has published a lot of the work. Azad has published some of the very first measurements we did in liquid extraction, and Uvi is starting to look at some equilibrium and kinetic studies of liquid-liquid interfaces. Zach has done a lot of the work with the Langmuir trough that I'll talk about today. And without their efforts and hard work, none of this would be possible, because these are very time-consuming, challenging experiments to make. The general idea of what we're going to study is really understanding the design rules for self-assembling materials, and then understanding how those rules might apply to something like a chemical separation. So in addition to the postdocs that I'm lucky enough to work with, I work with a lot of scientists who do neutron X-ray scattering, synthesis, soft matter electronics, MD simulations, characterization, synthesis. Like, it's a team effort. So all these things, it's you know, you have bespoke molecules, bespoke instruments, all these things is to study very specific aspects of the self-assembly. So our group in general can be summarized as really understanding hard problems in complex and time-evolving systems. So we develop instrumentation and tools that focus, generally speaking, on nonlinear spectroscopies that are designed to target certain interfaces or chemical processes of interest. Of those are liquid-liquid interfaces and mineral liquid interfaces that we're funded to do in the context of separation science. But these tools have found their way into imaging biosystems using nonlinear microscopies that we develop. And then we're looking into the idea of using quantum light microscopies to image things at ultra low light. So this is something that's a growing field that we're pushing into, the developments we make. We study collective and coupled dynamics across scale. So this is things that inform on chemical selectivity. These are the very femtosecond, picosecond processes that dictate whether or not a bond holds or breaks. And then how those events and processes on the ultra-fast molecular scale translate to the macroscopic scale. So we do all this through the lens of, generally speaking, vibrational spectroscopy, and using multiple light matter interactions to probe the things we want. And I'll explain what some of that means as we go forward. What is happening? Come on. Next slide. Next slide. Okay, let me stop sharing and then reshare. Because apparently there's a hiccup here. Okay, so we're back. So a lot of the science we want to understand revolves around chemical separation. So the idea of a separation is you take something that's in a mixture in one bucket and you want to move it to another one without all the other stuff. You want to target one or two species or a collection of species. So we do a lot of chemistry of liquid interfaces, and that's what I'll focus on today. We do chemistry at, like I said, mineral aqueous interfaces for rare earth mineral froth flotation. And we have a new project on CO2 direct air capture, where we're trying to understand the role of interfaces on CO2 transport and conversion. So the talk today, my goodness, this is going to happen on every one of these. There we go. We'll focus on liquid-liquid interfaces. So the reason we're interested in liquid interfaces is that they host unique functionalities, right? So you can have molecular self-assembly from either an organic phase or an aqueous phase, and the molecules that approach from the different phases, be it micelles in an organic phase or an aqueous phase, they'll assemble in different ways depending on how you introduce them. So you can have situations where you have your amphiphile in an oil phase or an aqueous phase, and you get different results in the assembly. So we're interested in understanding the rules for self-assembly and how those then apply to chemical separations, where self-assembly is the first step in extraction, where then you bind metal ions or anions or whatever you're interested in to then affect a transport across the interface to perform a separation. The presence of nanoscale objects at the interface and interactions beneath the subphase So you can have a nanoparticle interacting with molecules in an oil phase. You get different results. You get different templating effects depending on how you introduce these species from the two phases. And all of these things tie back in. And our work originally started by trying to understand hysteretic behavior in what's called droplet interface bilayers, where you can essentially allow, facilitate learning is what people call it, where you can impart molecular memory by pulsing in electric fields across an interface to insert ions, or you can induce mem-capacitive behaviors. The idea here is you can either facilitate growth and function, or you can depress it depending on how you time things and what the chemistry at the interface is going on. And this involves explicitly the role of aqueous phase ions and oil phase molecules. So the problem in probing these interfaces is that while interfaces are complex, thin, and they're dynamic, right? So an interface is intrinsically asymmetric. You have molecules that are aligned at the interface as you go around. So it means you have incomplete solvation. You have charged species at the surface. Those will have double layers. They'll have orientation and ordering that will take place that are important to the function of the molecules at the interface. And they're really thin, right? So if you move a monolayer away from the interface, it's not the same thing anymore. And this is really on display with things like water, where as soon as you move a monolayer to away, it's bulk water. So you have to be able to have sensitivity to probe those interfacial species specifically. And then a lot of the processes you're interested in studying, they're dynamic. They're not going to sit around and wait for you to make a measurement, right? So you want to measure an extraction, that's a non-equilibrium process. You have things assembling and moving all in real time. So you have to have time resolution in order to capture those processes you want to understand. So to do this, our approach is to use surface spectroscopy. So some frequency generation is the tool of choice for everything I'll talk about today. The idea is that you use the asymmetry of the interface itself to generate signals that are selective of the interface. So remember I said that all the molecules at a surface are aligned in some manner, depending on the alignment of that. When you have an intense optical field incident on the sample, you can induce a polarization in those molecules that will oscillate together that will then radiate light at this a harmonic or a sum or a difference frequency. Since those molecules are aligned at the surface, those oscillate together in phase. That phase relationship then constructively interferes in your detector and you get large signals. The opposite is true for bulk molecules. For every molecule you pointed up, you have one next to it pointed down. So those generate signals that are now out of phase with each other and they destructively interfere. So it's a very convenient way that you can use the asymmetry of the interface to generate something that's selective of it. The old school way to do this is to scan a laser beam across your frequency axis. This is, in this case, wave numbers. And when you're resonant with an IR transition, you get enhancement in the signal. Through a second interaction, through a Raman transition with a near infrared or visible light, you generate your second order polarization that then emits at the sum frequency. So because you have two field interactions on the input, the signal is surface selective. What we do is instead of scanning the incident wavelengths, we put in all the colors of light at once. So we use a femtosecond pulse of light that's broadband that excites all these vibrations at the same time. The upconversion pulse upconverts all those at the same time, and the spectrometer then resolves the contributions. The benefits of this are that it eliminates bulk contributions. It's coherent, so you can detect things pretty quickly because all the molecules at the surface interfere with each other in a constructive or possibly destructive manner. That gives you big signals or dips in the response. You get chemical information because you get a vibrational spectrum. You can look at these things like an infrared or a Raman spectrum, where it tells you something about the chemical groups that are there. And because we have control over the optical fields of the input and output beams, you can get information about orientation or help with band assignments. So you can really definitively figure out what's happening at that interface. And because we use femtosecond pulses, you can, in principle, using an excitation, probe dynamics from femtoseconds all the way up to hours. It's just your imagination and patience will be tested depending on what you want to do. So like I said, our group is really big into developing the techniques to do these sorts of things. So probing liquid interfaces, liquid-liquid interfaces is very challenging. It requires a lot of specialized instrumentation where we use laser pulse shaping techniques to variably control the upconversion pulse width that changes your resolution and your signal levels, collinear excitations, and then techniques to collect these things reproducibly using motorized wave plates, stages, things like that. So it's very important that all these things kind of work together, or else this is a very miserable experiment to make, more so than usual. So I won't go into all the details here, but I can talk about this. We do a lot with development of tools. So how did I get started in liquid-to-liquid interfaces? If you asked me in 2017, which is when I talked to Pat Collier, my colleague down here, about this, I would have said, there's no way I'm going to do this. This is too hard. I need something easier to do. But he convinced me because he had a really interesting system. So he makes these droplet interface bilayers, which are just 2 water droplets in a bath of oil, right? And he puts lipids in the oil, and you can bring the 2 droplets together with electrical leads in them and apply voltage across them, and you can induce nonlinear electrical signals. These are like MEM capacitive or MEM resistive effects. And what one of these MEM elements does is essentially just a variable capacitor, a variable value capacitor or resistor, depending on the previous value. So it remembers what its previous value was. So there's some molecular memory involved. And I thought this was kind of neat. The problem he has is that the lipids themselves degrade. So lipids aren't very stable, not for long periods of time. So he's trying to move away from lipids into an oligomers type sample, this ODMS, MIM. So it's a methylimidazoline head group with a polydimethyl siloxane. It's an oligomer. So this is N is equal to something like 14. Sample at the liquid-liquid interface. And what he found is that at low salt concentrations, he can bring these 2 droplets together. And if you wait long enough, they'll self-assemble and you can form a bilayer. And you can sense that with the current on the measurement. At high salt concentrations, you can bring them together and they never assemble into anything. You have to apply a voltage across it to drive that assembly. So what they did was they took some surface tension measurements and they showed that, okay, the high salt concentration, you have the fastest assembly of a monolayer at the liquid interface. But you have a barrier apparently to forming a bilayer. Whereas at lower salt concentrations or no salt concentrations, you have much slower assembly, but you're able to then form a bilayer much quickly. So how is it that you can have salt speed something up in the assembly of a monolayer, but then slow it down in the bilayer formation? So he asked me, can you look at the liquid-liquid interface? And because he's done me some favors, I did him a favor and I was like, okay, I'll give it a try. So what we did is we took this molecule and we dissolved it in hexadecane, which is his oil of choice. And we had to make a very thin layer of that. And it just so happens that when you put this molecule in hexadecane, you deposit on the surface, it spreads out very nicely into a very thin layer of oil decorated with ODMS at the surface. So when we took a spectrum, I got peaks that look like this. So these different letters are different polarization combinations. It just tells you something about the assignment and the orientation that I'll talk about later. And we want to know, okay, is this real, right? There's a 1 peak here, and there's 1 peak there. This is very simple. So at first I was thinking this isn't probably real. So we did experiments where we looked at oil and water, and we get very different spectral responses with much, much, much lower signals. So we know that this should be very weak because oil is not going to order well on the aqueous subphase. And we put a very thick layer of oil with this ODMS oligomer in there. We get a very different spectrum than what we have at the liquid-liquid interface. So we know from these control measurements that, yeah, we can probe the very liquid-liquid interface, and that this molecule is particularly good because it's got a spectral signature that is unique from the oil, water, or the aqueous, or the oil-air interface. All right, so what we did is we did perform some experiments where we changed the salt concentration. We went from that 0.1 molar to 1 molar. And what we find is that the amplitudes change depending on the ionic strength. So remember I said that SFG is something that probes symmetry. So if you have a structure at the interface, it's becoming increasingly centrosymmetric in some fashion. It could be forming what we call mushrooms. This is where you have a head group stuck in the oil phase, and this tail can flop around that samples some sort of volume, like half of a sphere. That's like an exclusion volume. So these things can flop around at the interface. As you form smaller and smaller and smaller mushrooms, or you have structures that are increasingly centrosymmetric, your SFG signal should go down. So what we see with sodium chloride, if you actually fit the data, the intensities, the amplitudes, or the areas under the peak for this CH symmetric stretch for the tail decreases. Correspondingly, so we have a line width change, where the line width gets narrower. So the line width samples something about the different environments that are sampled by those functional groups. So as you have mushrooms or structures that are increasingly centrosymmetric and tightly packed, you're going to have less inhomogeneous broadening because they have less instantaneous local environments that they're sampling. So the change for sodium chloride was modest. You had to fit it to see it, but it was statistically significant. You go to iodide, and you can see a huge difference. So there's something interesting here about iodide, and that it's more surface active. So we were wondering, well, what's happening when you go from sodium chloride to sodium iodide? Or is this even really something that's real? Is this a real effect? So the question we often get, and it's a good question, is how do you know this is actually what's happening? How do you know you're forming these centrosymmetric structures? So we figured the easiest way to do it, which in hindsight probably wasn't the easiest way to do it, was to actually resolve the process in time. So what we do is we take our oil layer, we take our aqueous phase, and we deposit the oil on it and start measuring immediately after the SFG response. And what we get at early times is signatures of hexadecane. So these are CH2 and CH3 stretches here that are not resolved, and then a Fermi resonance. This is what we see at the oil water interface, same sort of thing. As time goes on, we start seeing that the water signatures change, right? So over here, these are vibrations that correspond to OH stretches. So the OH stretch goes from anywhere between 3,000 to 3,600 wave numbers. As you start filling up this interface, this liquid-liquid interface with charged and imidazolium head groups, you're going to polarize bulk water molecules. So those polarized water molecules now generate SFG, right? This is known as the Chi3 effect, where you can generate nonlinear surface-specific signals from bulk species in the presence of an electric field, static electric field. And that field comes from the charged head groups. So as time goes on, that ODMS signal increases, and the definitive proof that what we're forming is increasingly centrosymmetric structures is that it peaks at around 10 minutes, and then it starts to decrease. And then it reaches some steady state where it doesn't move a reasonable amount for a very, very, very long time, up until the sample degrades or evaporates. So we know that what we're forming mechanistically is you have a micelle in the oil phase gets dropped onto the surface, right? It displaces the oil, and it forms a loose packing of those interfacial molecules, right? That is now charged. So it went from an interface where you had water oriented in one way to one where it's oriented in a different way and is now polarized. As time goes on and you keep packing in more and more stuff, those signals become smaller because these things are assuming more and more centrosymmetric structures. They're packing in tighter and tighter. These could be the mushrooms, which we originally hypothesized, or it could just be much more rigid, vertically standing tails. We don't quite have a good answer for this. At this point, MD simulations sort of seem to indicate, as I'll talk about later, that they stand maybe a little more vertically, depending on how you prepare things. So what does this tell us about the problem we had originally? Is, well, what ends up happening is you form the monolayer very quickly, but you form a monolayer that's so dense that it has a hard time interdigitating with each other. So these tails don't want to intermingle with each other to form a bilayer because these things are packed in so tightly. So salts are good in forming an interfacial monolayer, but they're not necessarily very good in forming a device using one of these dips. So what they're doing now is they're working around this idea of ionic strength to make these devices better. But what we thought would be interesting is let's take this idea of the chloride and iodine behaving differently, and let's try and tune some of these interfaces using the ions, right? So these differences suggest that we can tune the oil phase interactions. Or the interactions of the tails in the, I'm just moving that. The interactions of the tails using the ions in the aqueous phase. So salts, generally speaking, when you take a general chemistry course, salts are all kind of the same, right? They dissociate completely. At an interface, things are a little bit different, and salts are not that simple. At the interface, you have this electric double layer. It's where you have ions permeate into it and screen charges. You can also have ion pairing. This could be contact ion pairing, solvent separated ion pairing, where you have actually the ions getting right next to each other, and that affects some of the assembly behaviors. And the solvations of ions, these interfaces, is quite different. You can have molecules or atoms or ions that will either salt things in, they'll make structures, or they'll break structures. So what we thought we would do is let's try a family of ions across this Hofmeister series, where you look at things that bring in very strong hydrogen bonds. They have to pay a large energetic penalty to shed. And then let's bring in things down here like thiocyanate that goes in and just disrupts stuff, right? So those are gonna bring in hydrogen bonding breaking functions, right? And the idea is that because the interface is asymmetric, solvation there is gonna be weird. So you're gonna have strange things happen with the interface as you load up with these ions. So when we did these experiments, we weren't expecting to see necessarily all that much, but what we found was some striking differences in the SFG response as a function of the salt, as a function of the concentration. So if you look at something like chloride, you have, your predominant peak, and then you also have these side peaks. We've gotten better at making these measurements since the very first one, and these are related to the connectors and the terminal groups on the ODMS. But you look at something like the phosphates or the thiocyanates, you have very different spectral responses. The peak intensities, the phases of these resonances, and the contributions from water are all very different. So the idea if a salt was just a salt, everything would look the same, and you wouldn't see any differences. So the fact that you have anions now apparently changing the structure of the tail across the interface suggests there's some sort of interaction with those ions in the head groups in the aqueous phase that's more important than just purely electrostatics. So when you think about what these ions are, you have hard ions that bring along their own hydrogen bonding shell that are tightly bound. So these things are, generally speaking, not very surface active. So fluoride and phosphate don't really want to go to the surface because of the energetic penalties to removing those water molecules. So as these approach, you can have at low concentrations, you can have some charge screening that'll allow the ions, these head groups, maybe get a little bit closer. But it wasn't until we turned to MD simulations where we looked at the distance that imidazolium versus an anion can take at the interface, and we find that the fluoride is, generally speaking, not there. That's sort of what we expected. And if you look at the amount of water surrounding the head group, you find that there's quite a bit of water still surrounding the head group of the imidazolium, right? So the fluoride ions, they go weakly to the surface, and they don't do a lot to disrupt the hydration state of that head group initially that's around the imidazolium. As you move on and you look at the imidazolium and midazolium distances, the closer these are together, the more tightly they're going to pack, the more centrosymmetric those interfaces have to be from just these tails standing up, packing in together. So increasing centrosymmetry, we find that for the sodium fluoride, you have the least amount of molecules that are at the tightest distances possible. So what this tells you is like at high concentrations of a hard anion, you can force it to go somewhere near the interface to help screen. And we see that with the water changing, the water spectrum changing. But the response of the tails, you're not going to get that dramatic of a response because you're not enabling these things to really pack in super tight. However, if you go to the soft anions, what you'll find is that you get very different spectral responses. For something like thiocyanate, what you get now suddenly is the imidazolium and the anion are really, really good buddies, right? They're very close to each other. You have a large density of those interactions, which we think are ion pairs. If you look at then the amount of water surrounding that head group, that changes quite a bit too, right? So now this thiocyanate, because it's near the interface, it's near this imidazolium, dehydrates that head group, right? So when you do this, you're forming some sort of an ion pair that now allows at higher concentrations more and more of these oligomers to pack into more and more dense structures at the interface. And you can see that for the thiocyanate, you get the highest density of imidazolium and midazolium distances right around for the case of thiocyanate, high coverage. So this is an evidence for ion pairing. This is all very qualitative, right? We're talking about changes in some of the signals and the intensities. We started moving beyond this a little bit. I don't have time necessarily to go into all the details of this, but we're building a model where we can take the orientation of these methyl groups on the ODMS, and then each one of those has a tilt angle and a twist. So we're able to simulate the tilt and the twist angles for different polarizations. We can extract intensity ratios, and from those we can use vibrational signatures in two different polarizations. We can use the SSP polarization, which probes on the symmetric stretches of the methyl groups, and the PPP polarization, which probes on the asymmetric stretches. And the ratio of those gives us an idea of how these molecules on average are tilting. So it gives you in a way to now start quantifying differences in structure that can be compared more directly with MD simulations beyond just qualitative talks of packing and pairing. So this is in review right now. I don't have time to go into this, it's mathy. But what we wanted to understand was, okay, we can control the chemistry in the assembly via the aqueous phase and ion interactions. But what we haven't really talked about is the oil phase, right? We've kind of neglected that at this point. So what we did is a postdoc working with me, Zach, decided he was going to make a measurement where he wanted to form a monolayer at the air-water interface of ODMS. So what he did is he deposited some ODMS on the surface in chloroform, waited for the chloroform to leave, and then we measured the SFG signal. And to our surprise, he didn't measure anything. Apparently, this is found in examples of looking at polymers, PDMS, at air-water interfaces. It's not until you start compressing this thing that you start getting signals. So that means the molecules that are sitting there, they're sitting there. You could still get very weak signals from them, but they're in general, they're rotating around and they're isotropic. You're not getting a lot of signal. It's not until you start squeezing them together that you then get a sudden phase transition to get some sort of ordered interface, right? What sort of surprises about this is when we went to simulations, the ODMS molecules is from our MD, we're laying down, right? So the expectation we had, which is probably naive at the time, would be that the ODMS was hydrophobic and it was going to stand straight up. This is what we had in the oil phase, right? It was going to stand away from the oil. It did not want to be near it. But at the air-water interface, it turns out that air is a bad solvent, and it would rather be laying down at the water interface to at least get somewhat stabilized via hydrogen bonding with the oxygen atoms in the backbone with water. And what's interesting as you compress this, you start forming these aggregates or these assemblies where you have the tails start to solvate each other, right? So they still don't, these ODMS molecules still do not really like the water, and they would rather interact with each other. But it's not until you start packing them in together that you can really start seeing signal. And this is where you start getting ordering that we then see in our SFG response. So this is a potential way to generate differentially packed bilayers for DIBS measurements. So when we change salts, just like we had before, you're in a situation where you have different ions will mediate the assembly differently, right? So you have things like the hard anions, sodium fluoride, you end up getting SFG responses that look a lot like what they did before. For the case of 1 molar sodium thiocyanate, you end up getting really strong coupling between vibrations. So these things really allow the molecules to pack in much tighter. So this is something we have in preparation. The analogy here that it's analogous to liquid-liquid interfaces in that ions or salt effects are still playing a role in the assembly, but what is assembling is something fundamentally different than it was at the liquid-liquid interface, which is kind of neat. And what was surprising is as we compress these things, what we would find is that for the salt-free system, we would get a dip in the SFG response just before you have that onset of the phase transition. So remember, SFG probes symmetry. So as the signal decreases, that implies that your monolayer is becoming increasingly symmetric. So these tails of the ODMS are spinning around at the interface. You have some weak ordering. At some point, you have to shed a hydrogen bond that's formed between the ODMS and water. So at some point, as you get these molecules closer and closer and closer together, you have to force off those water molecules that are bound to it. Even if they're weakly bound, you have to pop them off. And then as soon as you do, then they can assemble into a monolayer. So that's what we see for the zero salt case, or for the case of fluorides, right? Fluorides seem to inhibit the assembly and that they're at the interface very weakly, but what they still require you to leave that hydrogen bonding network behind. So the shift at the surface pressure you have to reach before you form assembly is higher, but you also see that same dip. You have to pop those ion interactions off before you're able to form one of those assemblies. So you don't see that with the soft anions. In fact, for things like thiocyanate, you see that has the earliest onset. So the disruption of a hydrogen bond network for thiocyanate enables the assembly, but the resulting structures are maybe not necessarily as ordered as they were for fluoride. So it's not always about just disrupting hydrogen bonding networks as being good. It depends on what you want to make. You get differences in the equilibrated structure, especially at the air-liquid interface. So our simulation results show the same sort of thing, but there's a difference. It's as you start compressing these together, you start having to change the amount of water that can be bound to the ODMS versus that in water. So this squeezing out effect, where you're physically pushing out water molecules to enable new interactions between tails, the same sort of effects that result in the mem-capacitive behaviors of these materials, where you have oil between the bilayer moving in and out of the bilayer. Here you have to have water moving around. So the question is can we generate maybe mem electronics with water? This is something we're pursuing in parallel in a different setting. So the question is, okay, we've done all this stuff about assembling and controlling a very simple system, right? This is one tail, one head group, changing just ions. What else can you do that's a little bit more complex? So we want to understand chemistry of liquid extractions. Ultimately, that's what the funding is for. Ultimately, that's a very complex problem that involves chemistry going from a neat interface to something that's quite messy. And the questions we want to ask are, where does the selectivity take place? Well, we know it's at the surface, but what are the processes that the molecules have to undergo in order to affect a selective chemical separation? You want to bind one metal or one family of metals, somehow form a complex that can then transport into the bulk organic phase. So these are non-equilibrium processes, and they happen over a huge range of timescales. So laboratory timescales, that's like you have transport phenomena, coalescence. But then there are processes in the femtosecond, picosecond timescales that define things about recognition and solvation, bond making, and breaking. So the work I'll talk about today generally focuses on the laboratory scales, but we have some results somewhat recently probing femtosecond, picosecond processes and trying to relate those back to macroscopic phenomena. So the motivation for understanding liquid extraction chemistry is that the periodic table is full of stuff, and some of the stuff is more valuable than other stuff. And those things like cobalt, things like rare earth elements, are usually dominated by a single country. So most of the world's cobalt comes from Congo. So it's bad when one country has all of the resources. It makes the United States Department of Energy antsy, and then they fund projects to figure out how to get it in other ways. Rare earth elements are no different, right? They're everywhere, but they're in such low concentrations that they're not viable to extract. So ways in which to extract those would be energy efficient. It would reduce cost locally to get them, reduce our reliability on other countries, et cetera. So we want to understand liquid extraction because that's the industry standard. That's the way that industry prefers to separate things because they have the framework to do so. So the question is okay, what governs the selectivity, right? You want to pull out just cobalt, right? Or just nickel or just manganese. Well, you can start with a ligand. It's an amphiphilic ligand. This is D2EHPA. I call it DIPA. Other people call it HDEP. It's just a ligand, the phosphate group. And you can functionalize it like crazy. You can add on oxygens, branching. You can change the head group. And if you look at the extraction efficiency of one of these ions versus pH, which is the most important handle to control in an extraction, generally speaking, you get dramatically different extraction curves, right? So changing something seemingly as innocuous as a tail gives a huge difference on the extraction efficiency and where it extracts and what pH and how selective it is. So there's lots of different handles to control. The things we're going to talk about today, given the time, we're going to focus, generally speaking, on ligand, pKa, some about ion effects and tail composition, along with the fact that the oil phase is going to be important. So to understand the mechanism of solvent extraction, we do the same experiment we did before, where we have our molecule, DIPA, absorbed into oil, placed onto water, and we can change things like the metal ion concentration of electrolytes, or the pH, right? So like I said, the most important thing to consider when doing an extraction is what is the pH. And if you look at the pH, the extraction percentage for cobalt of this molecule into hexadecane is a function of pH. You get some extraction at pH 4, 5, 6, 7, etc. But if you look at the SFG spectra over that same range, pH 4, you have very little ordering. pH 5 and 6, you get big ordering, right? That makes sense because now it's where you're extracting. And then pH 7 or whatever, you should get a whole bunch more extraction. And it turns out that the SFG signal goes back down. So it's very odd to have signals that increase and decrease in chemistry, right? Having something that's periodic is strange. So what this led us to do was, okay, what is the pH actually doing and what is it doing over a wider range? So we took SFG spectra now all the way from pH 1 to pH, I think 7.5 in half pH unit increments, and we took it in different polarization combinations. And what we see is you get a lot of peaks, and those signal intensities vary a lot depending on the specific pH you're at. So there's a lot to unpack in this. So I'll just briefly say that we can do some analysis, and we get out information about population, packing, and ordering, and that's will be talked about here. Packing efficiencies and orientation support the claims we will make. I won't talk about them specifically, but then we also get changes in phase. And phase reports on something about electrostatics, and I'll go into that. So what the data suggests is that as a function of pH, your signal increases and then decreases, and then increases again and then decreases again, right? That's a very peculiar thing. And I didn't believe it until we measured it probably 20 or 30 times, this pH 4 particularly. And we see that the amount of signal we get from the DEPA, which is the tails, is larger here than it is the water. Over here, they're more comparable. So it tells you there's these different regimes where you have different assemblies, different ordering of the ligands in the water in these two different windows. So what we need to do is understand and build a molecular model of what the interface could be doing. So if we build a very simple chemical model, you start with a protonated ligand. It has an acid-base equilibrium constant to form the deprotonated species, right? The protonated ligand at low pHs will dominate, right? Because you have a bunch of excess protons. But then right around the pKa, you should get a changeover where you start getting now liquids or ligands and then their deprotonated form, right? So as you keep going forward, we notice that if you shook these things up, you would get a cloudy phase sometimes, and that suggests that there's the presence of small aggregates. It wasn't really cloudy, but you could see that it wasn't as clear as it was to start. And that has an aggregation pKa of something around 3.8. And you keep going and you start getting something that's kind of like an emulsion-y type thing. It's just really goopy stuff that forms the interface. And that's something you see at high pHs pretty often. You start forming these large aggregates and stuff. So taking those together, and you can plot the persistence of these things at different pHs. So in this window, we have a situation where we have predominantly monomers, ligands deprotonated. Over here, we have a window where we have small aggregates. So you have two regimes, right? You have a molecular absorption and then something about aggregates are clustered. And this is supported by the orientational analysis and packing analysis that we don't have time to talk about here. What's interesting is that the phase of these samples, these signals. So there's this contribution I mentioned earlier about chi3 from charged interfaces. So you have resonant contributions that are due to transitions between real vibrational states. But then you also have this chi3 contribution that arises from the surface potential set up by the charged species at the interface. This phase term mixes this chi3 contribution in, so it heterodynes it into the signal. What the important thing to note about this is that you get SFG spectrum that will shift quite a bit. You'll have this contribution from this non-resonant chi3 effect affecting your signals that you have to take into account. So you can change your phase, your surface charge density a little bit across a small window, and you can get different SFG responses, especially in the low frequency regions. So it's important because that's where we do a lot of our measurements, is in this low frequency OH stretching region. And if you look at the phase angle as a function of concentration, it goes up, right? So right around pH 5, where you have all of your ligands are deprotonated, you have these aggregates, you have the surface, highest surface charge formed. What this means is that you have a different hydrogen bonding network set up here at the higher pHs than you do at the places where you have molecular absorption, right? So this tells you, one, you saturate your surface charge, which you should, and that the hydrogen bonding networks are going to be important. So the hypothesis we have is, well, what are these aggregates? Well, what if they're made up out of our DEPA ligands, but now they're bridged with water molecules, right? So in some instances, you have water solvating your head group. In other ones, you have these things bridged in some sort of fashion. So if we look at our OH spectral region, this is a zoom out of our data. What you'll see is as you change the pH, your signal will go up and it shifts over to lower frequencies. That's characteristic of stronger hydrogen bonding interactions that take place. And that peaks right around pH 4.5, 5, 6, right in here. And then as you go to higher and higher pHs, that drops off again, right? So everything is consistent, no matter how many times we measured it, it was always like this. And what we thought was, okay, well, this is interesting. Do we have any proof that this is due to these stronger hydrogen bonds? Now we look at the work of Paul Peterson. He showed that in the DNA backbone, just a bunch of phosphate groups in it, you can have a chiral spine of water. So those vibrations can be isolated with SFG spectroscopy. And you see this strong absorption right around 3200. It's low frequency OH stretches. This is exactly what we see here. So it's not as clean as his because he's looking at a chiral response, but we see this shift to lower frequencies of OHs. So this is nice circumstantial evidence, but what we really want to do is know that what we're looking at here is our aggregates. We really want to understand if water really is bridging these things together via hydrogen bonding. So the easiest thing to do is just to edit out the hydrogen bonds, right? So take your DEPA and replace an OH with an H, and that should get rid of all the hydrogen bonding bridging. And when you do this and you look at the SFG signal as a function of pH, you find that there really is no ordering ever. These things never order. There's no bridging. There's no water ordering. As you expect, this molecule doesn't do much. So what it means is that the physical picture we had before is good. At pH 3, we have molecular-like adsorption where the molecules are solvated in the normal way. But at higher pHs, you have water that's acting as interfacial glue, sticking these things together into aggregates. At pH 4, we don't quite understand what's happening there. We've done some experiments to try and figure things out since. But there seems to be a crossover in between the molecular-like adsorption and this aggregate formation. What we wanted to do was, from here, understand, okay, can we affect this ordering in some way and get some insight into the extraction chemistry? So what we did is we made a measurement in the presence of cobalt. And we find that with our SFG measurements, we get tails ordering nicely at early times, but then everything starts decaying over time. So the measurements we make are fast enough that we can extract, measure changes in time. To our knowledge, it's the first time these measurements have been made. Mark mentioned earlier that we're not the first ones to do this, but we think we are the first ones to measure such a process in time. And we see evidence, obviously, for time evolving interface. So the first thing we expected was, well, this is extraction. This is great. Let's write a paper. But then, you start taking a closer look at it. It's like, well, it could be something else too. So we have to do some experiments, right? So we changed the concentration of cobalt to DEPA. So as you move from left to right, you go to higher amounts of cobalt. And we changed the pH. So a few things jump out here first, right? So the rates are different depending on what you look at. So as you increase the amount of cobalt, you'd expect phenomenologically that you would have faster rates, right? You have more stuff in one phase. Your apparent rate should be faster, but it's not, right? All of these rates are mass transport limited. So it's very dangerous to start and pull out something like a rate constant. And additionally, these things don't necessarily follow the phenomenological rate. This should speed up, but it slows down. pH 4, you'll recall, had no ordering before at all, right? But as soon as you put cobalt in, suddenly your signal is large. It's ordered. And then that evolves in a more phenomenological sense, whereas as you add more cobalt, the rate apparently increases. So what we think is happening is you have cobalt, in the case of pH 4, inserting into the hydrogen bonding network that's there or that isn't there and ordering these things via cobalt bridges. Same thing's happening over here at these higher pHs, where you're having cobalt inserting into the hydrogen bonding network and changing things around. The interesting thing is in every one of these cases, the amount of ligand that's ordered, the amount of water that's ordered, and its decay in time is all different. So in every one of these situations, you're forming something different at the surface and it's doing different stuff. So liquid extractions are notoriously complex because the interface mucks everything up and it looks like the interface really is messing everything up. So every single instance you look at here, you have different structures and species that are formed. So we wanted to understand is the decay of the SFG due to extraction. So you could look at intensities and divided by widths that represent something about how much stuff is at the interface. But the key thing here is that at the interface, this phase angle, if you were having some sort of extraction, you'd be at a steady state, right? So at very low pHs, at pH 4, low concentrations, you have a phase angle that represents some sort of setup equilibrium charge, right? What we find is that pH 5.5, where you had the largest decay, you get a big change in the SFG response via the phase. This tells you that whatever you're forming at the interface has different electrostatic properties than what you have at an interface where you have a higher pH or a higher loading. So this tells you that whatever you're forming some aggregates here, these are probably things like micelles that stick around the interface that are somewhat charged. This is something we can't actually probe with SFG. So right, SFG is a great tool for a lot of things. It's not great at probing structures, right? So a lot of the X-ray work that's done out there, very complementary to this. This is a problem we'd like to figure out. SFG is not great at this. So we can only speculate that it's due to some sort of centrosymmetric structure that's being formed. And this is based on work looking at very similar molecules in cobalt, where they see these thin rod-like polymers, these micellar type structures using sands. And of course, Mark has done a lot of great work using X-ray measurements to suggest like a budding mechanism for divalent ions with the same sorts of molecules. So we think what we're forming are micelles at the interface that are kind of sticking around. They have different charge characteristics. But what I'll note is all of these things are generally speaking undesirable for separations. You don't necessarily want to work at a concentration that's high in ligand or high in ion concentrations because you end up getting this aggregate stuff. You want to extract as a molecular system to get selectivity. So what we thought we would do is, well, let's try and find the region where these molecules behave in concentration-wise as monomers. So you can measure an absorption isotherm where you change the concentration of ion or ligand. This is all at 1 molar sodium chloride, pH 5.5. And if you plot the SFG response versus concentration, you can get out an isotherm. This tells you about the free energy for absorption of these molecules to the surface. And for DEPA, we get an equilibrium value, some equilibrium constant, a delta G. You can extract things with surface tension where you saturate the surface. This is all good, but we thought we want to compare it then to a molecule that's the same number of carbons. We call this DOP, but it's linear. So it's got a linear chain instead of being branched, right? So this should have resulted in different interfacial structures. And what we find is that, well, we can still get kind of an isotherm, but we really can't get any points below. We can't get any points below 0.25 millimolar. So no matter what we do with this, when you put the oil down on the interface, it forms these little bubbles of oil that will not spread out below that concentration. You can do pendant drop measurements where you're forcing the oil into liquid, but we can't conduct SFG below this. So this suggests that these interfaces are saturated differently, and that stabilization of that liquid-liquid interface depends on the tail branching. So we did some additional measurements to see, well, what's really happening here? And we thought we want to compare with oil and without oil, right? So in the case of an oil phase, you have this hydrophobic interaction between the two phases that they don't want to talk to each other, right? So these ligands, these amphiphiles have to go to the interface, and essentially they're taking one for the team, right? They're going to spend half of their time in the aqueous phase, and their tails are going to stick in the oil phase, and they're going to block all that oil, right? So a molecule like DEPA, which is already very branchy and blocky, has no problem spreading out and assuming an orientation that can sate both the oil and the aqueous phase. As you go to higher and higher concentrations, because now you're trying to cram more and more stuff into that monolayer, you end up inducing curvature in that monolayer, and you get larger and larger packing parameters. So you end up getting a less ordered monolayer for DEPA when your concentrations above the saturation point. At the air interface, because you don't have to worry about the oil contacting water, these molecules will always stand up. So if you look at the SFG responses at high concentrations of ligand above the saturation, you get excellent ordering. At the liquid-liquid interface, you still get good ordering, right? You still have order, you still have more molecules here, so your signal is larger, but if you look at the packing, it's differently. And you compare it to air, well, the air-water interface, you don't get as much signaling. These aren't ordered in the same way. If you look at the peak ratios, these are fundamentally different structures that are formed than at the liquid-liquid interface. If you go to a linear chain, well, if you look at the air interface, these are perfectly happy to stand up, right? These don't have any oxygen groups like ODMS did that want to hydrogen bond. So if you look at the air-water interface, you get this blue trace, which you get more signal than if you look at the oil aqueous interface, right? These don't want to be, the oil and the water phase here don't want to interact with each other. So these DOP molecules are forced to spread out and occupy as much space as they can to try and block those interactions, right? So the SFG response is correspondingly bad. So the liquid-liquid interface here is actually making these molecules conform to really bad packing and orientational structures. As you go to higher and higher concentrations, now all of a sudden the signals increase very dramatically. The molecule stands straight up. They pack very well, and they pack much better than they do for DEPA or at the air-water interface, because now you have those oil molecules, the hexadecane, that can facilitate the organization. So what this tells us is that every one of these interfaces that we study is unique, right? You just can't make assumptions about one interface being the same as another. So you have to use relevant oil phases for specific extractions. So we're using hexadecane, which isn't used. So we need to start changing what oil we're using, going down to, I think it's dodecane is what people use for various processes, like Purex or Talspeak or something. So we need to change the oil phases that we're looking at, because the hexadecane, while it's similar to dodecane, isn't the same. And my concern is, and based on other DIBS measurements that have been made, you get differences in the solvation. So we're trying to explore other oils and how oils can be used to tune the assembly and the structures of these interfaces. So the question is what have we learned? Well, ion pairing is an important thing to look at in the oil phase, but don't overlook the oil phase solvation on the packing. The pH and water ultimately drive assembly at these liquid extraction interfaces, and the chemistry of these interfaces is remarkably complicated. It's not a one-size-fits-all sort of a thing. You have to really look at the details of each system. So with that, I will say that where we're going with this is more on the same thing. We're doing more of these soft matter electronics. We're moving into the multidimensional IR and SFG spectroscopy to study extraction of ions from more complex mixtures. So with that, I will thank you and thank everybody on the list here for contributing. I'm happy to take any questions.
Thanks, Ben. That was a great talk.